For this problem, we're looking at a sign, and this road sign has three loads which are acting. One is the weight of the pole, the pipe that supports the sign. Second is the weight of the sign itself, WS, which is acting there at the center of the sign, C, and also the wind load, P, which is acting in the negative Y direction with its resultant there also at C. What we want to know really first are what are the components of stress that are acting at 2 points, A and B. They're shown in the cross section there at this location there at B. And then once we have that, then we want to know the principal components of stress acting at those points there of A and B. As we've seen, it's really to our advantage to work with a three-step plan here in terms of determining our components of stress, where the first one is to look at the internal loads. What this means is when we make our mathematical cut through the pipe there at B, what we want to do is represent all the reactions, the internal resultants that we would have at such a cut. So at any cut in 3 dimensions, we will have at most 3 components of force and 3 components of moments. So I'm going to draw in all 6 of those. I'm going to draw in Fy like this. I'm going to draw in Fz, obviously along the z-axis. I'm going to draw the reaction component there of Fx in x. In addition to that, I'm going to put the moment about the x-axis, which will be actually a torque, so I'll call that Tx. I'll put a moment in the z direction. It's going to be a bending moment, so I'll call that Mz. And then I will have the bending moment about the y-axis, My. I don't know whether they're all going to be there or not, but we'll let equilibrium tell us that answer when we're done. For equilibrium, we're going to write our forces in terms of x and y, add those, and so what we have for the x direction is the reaction force there of Fx. We have minus the weight of the pole minus the weight of the sign, that is in x. In the j direction, I've got Fy minus the wind force P, and that's in j. In the k direction, all I've got is the reaction force there of Fz. There is no applied force in that direction, so that's in k. And for equilibrium, that is a 0. I can say here that Fz is a 0. The I components give us the Fx minus the weight of the pole minus the weight of the sign is equal to a 0. So we know that the reaction force in y is just the total weight. And summing forces in the y direction gives us an expected result, I think, in that the y component of reaction in y is equal to the wind force there, P. We'll also write down a moment equation about that cut point there, B. The moment in x, the way I drew it's minus Txi. I have My in the j. I have Mz in the k. And then I need to do an R cross F for the wind force and the weight force of that sign. So I need to go from B up to C, so this is going to be Li plus Hk. This is the vector which extends from, again, from B to C, cross with the force, so this is the weight of the sign and the wind force in the J. When I do the R cross F for this, what I end up with is pH in the I. I have a Ws times H in the J, and I have a minus PL in the K. Therefore, whenever I balance out my components, the I components say that minus Tx plus pH is equal to 0, so the torque component, the moment component there in x, is just p times the distance of h, and the j components give us the my minus ws times h. That's a 0, so the bending moment about the y-axis is ws, the weight, times the distance there of h, and the k component that says that the z component of m minus the wind load p, the distance l, gives us the bending moment about z is equal to p times l. So this is rather complicated. This is about as complicated as it's going to get, because we have three non-zero moment components. We have 2 out of 3 non-zero force components. So therefore we have to deal with a total of 5 resultant components at that cut. When we look at our stress distributions, we will have 5 distributions, one for each one of those. The first one I'm going to deal with is what I'm going to call tau 1. And tau 1 is going to be the shear stress due to Fy. So this is d over 2 over IP. Let me see here. Tau 1 is going to be due to Fy. So Fy, I'm sorry, I've got my torques and my direct shears a little bit mixed up here. So the tau 1 should be the shear stress of Fy. And we can figure out the A star y bar star divided by IT. And so let me do this in terms of magnitudes and end up putting the forces in the correct direction when we draw in our shear stress. So as I look here at that's going to be due to Fy. So the shear stress distribution is going to be in the negative y direction. So think about a shear stress that looks like this with its distribution looking like that. It's going to be a maximum there at B. It's going to be a 0 there at A. The next one of the 5 I will write down, it looks like, is the normal component, the axial component of stress due to the axial force there of Fx. And of course that is divided by A. Let me again just write down the magnitudes and get the right direction when I draw in my stress distribution. In fact, let me go in and write down all 5 of these before I go back up to the other pictures. Then I got sigma 2, which is going to be a bending one, due to the bending moment mz. The y value, if you will, is d over 2 divided by I. I'm going to write down the magnitude of that. I won't worry about the SIGN signs. Sigma 3 is the normal stress due to the bending moment my. Again, that's d over 2 divided by I. We'll take the magnitude of both of those. And lastly, there's going to be the torque, which I'm calling torque 2, which is due to, the shear stress due to the torque, Tx. And that radial distance is d over 2 divided by the polar second area moment there of IP, and I'll write down the magnitude of those. I've already done tau 1. Let me go back up here, scroll back up, and put on the other 4 components. The sigma 1 is going to be, in fact, let me draw sigma 3 for reasons which might be clear when I get through. Sigma 3 looks like this. Sigma 3 is the bending, the normal component due to bending, and the bending there for sigma 3 was my. So if we look, in fact, let me make a move here that I should have done right from the beginning. What I drew here was an FBD of the top part. It's easier for me to see if I draw now those equal and opposite reactions here on the bottom part, because I can actually see that face. So I've got Tx, the torque Tx. I have the axial force of Fx. These are just equal and opposite to the ones that are above. This is the Mz component. And I have the Fy. And I have the My. These are the 5 non-zero terms. Okay, so what I'm showing here is sigma 3. Sigma 3, I said, was the axial component of stress due to the bending moment My. So as I look at what My is doing to that face, if you put your thumb in the negative y direction, you're going to see over there at the side B that normal stress is compressive. On the opposite side, it's tensile, and of course there at A is on the neutral axis, so there is none. If I now draw in sigma 1, that's an axial component. So I really don't have a whole lot of space here, so let me lay that right there on top, where sigma 1 is going to be compressive. Its magnitude is the magnitude of Fx divided by A. This distribution that I drew over here first is tau 1. If I look at sigma 2, sigma 2 I said was that due to the bending moment Mz. And so if I come down and look at this, the bending moment Mz is going to be putting the A component in Mz is going to be putting A in tension, let me draw that in blue so I don't confuse it with that red. It's going to be putting A in tension and the opposite side in compression. So what I'm showing here in blue is the normal stress there is sigma 2. And last but not least here is the tau 2. And tau 2 is the shear stress due to the torque. So we need to look at the cross section in order to observe that. Look at Tx. Tx, putting your thumb in the positive x, it's going to be putting a shear stress direction of B in the negative y. That same torque is going to be putting a shear stress at A, value T2 in the positive z. So these are our 5 components: tau 1, tau 2, sigma 1, sigma 2, and sigma 3. Our task now is to put these together on our stress element that we have shown there. Our goal is to write down the components of stress, make sure we got them in the right direction on the correct face. So let's focus on A first. Point A, which is the point right here, what we see is that at A there's a tau 2 in the positive z. Okay, so I'm going to draw in tau 2, and as before I want us to focus only on the x face. We'll deal with the other 5 when we get through. So in the x face, tau 2 is pointing in the positive z there for A. Also for A we have a sigma 1 which is compressive at A. We have a sigma 2 there at A which is tensile, so with me drawing it the way I did, in fact let me change this. Let me draw this as a tensile one, and I know that sigma 1 then was compressive, so I'll put a minus sign in front. And since sigma 2 is tensile, It's going to be a plus sign, like that. If I look at sigma 3, no contribution. Here's A. A is on the neutral axis. I look at A for tau 1. There is no contribution because A is there on the edge. So that's all I've got. I've got two components of normal stress and one component of shear. If you want me to complete this, I would draw equal and opposite one like this, and then I would draw in my shear stresses like that. If I come over here to B, if I look at tau 2 first, tau 2 is pointing in the minus y on the x face. So tau 2 is going to be this way. If I look at tau 1 right here, that's also in the minus y there for B, so I'll have a tau 1 and tau 2. In terms of the normal components of stress, I've got a sigma 1, which is downward. I have a sigma 2. Sigma 2 is going to be a 0 because B is on the neutral axis. If I look here at sigma 3, that's this amount right there, it's also a compressive one, so that's going to be like this. Again, there's no sigma 2, but we have the other 4. As I complete my stress cube, I will draw in these. But again, first focus on the X face. I think that will really help you out, keep yourself focused on the right place. So that does our components of stress. We now want to write down our principal components. We've done this many times before. We know that we need to first find sigma average. So let me do point A first. So sigma average is going to be equal to, and that's going to be the sigma 2 minus sigma 1 over 2. And you can put in the expressions for sigma 1 and sigma 2 that we have got. So let me make sure I'm just consistent on signs and write it as I've done here, sigma 1 and sigma 2. We know that the R value, the radius of our Mohr circle, is going to be sigma 2 minus sigma 1 divided by 2 squared plus tau 2 squared. And we see that that's larger in absolute value than is sigma average. And then for B, I know that sigma average is just going to be simply sigma 1 plus sigma 2, sigma 3 divided by 2 with the minus sign in front, because both of those are in the negative, what the direction is that in the negative x. Sign's not that important because we know that that's going to be end up squared once we deal with R. And then we'll have our sigma 1 plus sigma 3 over 2 squared plus the tau 1 plus tau 2 quantity squared. That looks like that. And so for either case, we're going to have that sigma P1 is sigma average, which we have, plus R, and sigma P2, which is sigma average minus R, depending upon whether we're looking at A or we're looking at B. And please note that this number here is also larger in magnitude than is sigma average. So in summary, this problem was quite long. And it's long because with the loading that we have five out of the six possible components of load at the cut. We ended up having two non-zero forces, one an axial force, one a shear force. We had all three components of moments. We had a bending moment about y, we had a bending moment about z, and then we had a torque about x. So the key part, I feel, is always this right here. Can we draw in our stress distributions? If we can do that, drawing in the stress components on our stress element is relatively easy to do. Just look up at the picture and put it in there as shown.